one thing, one kind of behavior that you might see when you do Monte Carlo estimation is that you just sample, say, k different episodes, and then you estimate your value function, assuming that you know the value function exactly. So if you know the value function, so here v pi is the value function, v hat pi is the one which you get by, yes. But I changed the batteries already. You changed the fresh batteries? Yes, just I did it before the lecture. Okay. Because there was one box, one set here. Then it's fine. It's fine. Okay. Change location where you flip it. Ah, okay. To get better. Here? Yeah. And make sure it's not economic. Because of that, it's just heavy noise. Ooh. Is it now good? I'll check it. Okay. Okay. Yeah, thanks. Thanks a lot. So you're going to listen to a noisy video. Okay. Okay. So, yeah, here. So, if assuming that we have the true value function, and this v hat is the one which you get out of Monte Carlo estimation. Now, I mean, one point. This v pi that I'm showing here, I mean, obviously we don't have it, right? Because if we had it, we didn't use Monte Carlo, yes? So we use Monte Carlo simply because we don't have it. But for some dummy example, like the grid world example that I gave you, you can write that down, and then you can see how does Monte Carlo compute the estimate, right? If you do that, then you can find what is the difference between these two, right? Obviously, what should be the difference if you just sample, I don't know, infinite number of samples from the environment? Where should it go? It should go to 0, right? And then the more samples you have, it's going to drop, right? So you always see such a behavior. You start with huge error, like your estimate is totally nonsense. But gradually, your estimates start to get better, right? And there's always some value for k, which gives you a kind of guarantee that, well, you're doing well, okay? And that k obviously depends on the number of states that you have. But one thing interesting that you see, and you see it all across the algorithms in the model-free case, is such a behavior. The behavior is that when you are updating and you do the online update, that alpha value that you use each time you want to update, right? That alpha value, it has a sort of optimum. So it means that if that step which you are using to just fix your estimate in every sample, if that step is too large, your estimate is going to get bad. If it's too small, it's going to get bad as well. And what is the right choice of alpha? Well, this is something numerical. So it depends on your environment. You typically need to try different alphas, and then you just find out what is the variance for every single of them, and then you choose the right one. But the key point here is that this value of alpha is not like you increase it or you reduce it, you're going to see a monotonic behavior. It's a kind of convex behavior, and you need to find the right one. Okay? So that being said, now I want to use this idea of Monte Carlo to implement the policy iteration, right? Where should I use the Monte Carlo approach if I want to do policy iteration? So policy iteration has two parts, right? One of them is evaluation, one of them is improvement, right? In which of these steps I should use Monte Carlo? In the evaluation, right? Because once you had the evaluated one, you can't simply improve it, right? Improvement is nothing important. The key point is that you want to evaluate it. So I want to use Monte Carlo algorithm to do the evaluation. Now, the one which I showed you looks at the environment and finds the value function for you, right? Now, if you want to do the improvement, what do you need? Do you need the value function or you need the action value Go ahead. Action value function. You need the Q function. You don't need V function, right? Because Q is the one which has actions, right? And then you just take the one which has maximum value, right? Okay, now, in chapter 2, we really did not care about the fact that are we working with a value function or action value function, right? So we said you just find the value function, then you compute action value function. How did we calculate action value out of value function? No, it was not averaging. The other way around is averaging. Bellman equation, right? So if I want to get from the value function to the action value function, I need to use Bellman equation, right? So let's write down the Bellman equation. So that was the Bellman equation which we used in chapter 2. We said, like, you have the value function. Now, if you average the value function at the next state and you add it up with the immediate reward function, then you're going to find the action value, right? But now if I open up this term, then I'm going to end up with this expression. Like, I need to compute this expectation, right? And for this expectation, I need to know what is the transition function, right? If I want to know what is that expectation, I really need to know what is the probability of going from this state to the next state, right? And that is the transition function, right? Moral of the story, you cannot use Bellman equation here anymore. It doesn't mean that it's not valid. You do not have the probability function to compute it, right? So this is still the same problem. Any idea how I can resolve this? Can I use Monte-Carlo directly? I can use Monte-Carlo directly to estimate the action value, right? I don't estimate value function, just action value function, right? And for that one, again, I can do it, right? What is action value? It's just you know state and action, right? And then you want to see what you are going to collect afterwards, right? So you just start with one state, you do one specific action, and then you start to sample from the environment, right? This is one sample return, right? And then you just average them over all samples that have same state and same action, right? And this is going to be the action value. So this guy cannot be done directly, so we are going to just use Monte-Carlo to estimate the Q function from the samples. We're not really using Bellman anymore, because if we want to use Bellman, we need to know entity. We don't know it, right? This is a whole problem now. Okay, so this is the way that you can estimate action value. So let's look at one trajectory. This is one trajectory that I have sampled. I was in this particular state, right? I did action A0, and then the environment has taken me to a state S1, right? Then I kept on playing with my policy, right? After S1, I just played with my policy. I did A1, then I went to the next state. Again, I played with my policy, went to the next state, and so on until I got to the terminal state, right? Now, if I look at this one at S0 and A0, right, I have collected R1, R2 towards the very end, right? Correct? So if I add them up, this is one sample return given that I was in state S0 and I did action A0, right? If I have, say, 100 of those samples, then eventually when I average all of them, this is going to be an estimate of my action value function at the point S0 and A0, right? Everybody's clear, right? So same idea. Now instead of just thinking about the state, you're thinking about the pair, state and action together, right? Everybody's cool, right? Okay, so if you got it, then probably you can see that I really do not need to estimate only the action value for this guy, right? I can estimate the action value for this guy and the guy next and the guy next towards the very end, right? Because for every single pair, whatever I have afterwards is just what I collect if I am in that state and do that action, right? So this is not one simple, one single sample return. It's actually a bunch of sample returns, right? And you do the same thing. So what we do, we usually start with the action values to be 0. So we say like at all states for all actions, we have value 0. And now we start to sample, right? We just do one random trajectory. And you start from one stage, you do one action with your policy, and you keep on playing, right? And once you do that, then you would say, okay, maybe if I think about the very last one, like I want to know what is ST minus 1, AT minus 1. Okay, ST minus 1, AT minus 1, the action value here, one sample that I have got is actually G, which was 0, G, which was 0 initially, plus the return that I collected, the last return, right? And I update my estimate for that particular state action, right? And then I go one step backward and say, okay, what about ST minus 2 and AT minus 2? When I was at state ST minus 2 and I did action AT minus 2, I kept on playing with my policy, right? And then I collected RT minus 1, after that RT, and then it was terminal, right? So what I collected was RT minus 1 plus RT, which I can write it down, RT minus 1 plus the G that I had before, right? And this is the new sample. So I'm going to update my estimate for ST minus 1, AT minus 1 again, right? And then I go one step backward and keep on going till I get to the beginning of time, right? Now I have everything updated. I go for my next trajectory, right? I sample another trajectory. It's a new trajectory. And I again go over every single pair, right? And I update my action values. Now, if you keep on doing this for enough number of episodes, then you're going to converge to some action value function, which is, under some conditions, a very good estimator of your action value function. Everybody's clear? Same thing as before. Now you have action value, right? Now, one question. If you do this for action value, and you do the one we had before only for the states, just the value function, which one you think converges faster? The value, right? Why? That's correct. Why? Yes? Go ahead. Yeah, sure.
Because you don't have to worry about the actions as much.
Yes, because if you think, for example, you have, say you have 100 states and 100 actions, right? In the value estimation, you are just estimating 100 different values, right? So 100 values, each of them for one of the states, right? But if you have 100 actions, when you want to estimate Q function, you have 100 state, 100 actions, so you have 10,000 pairs, right? You're now estimating 10,000 parameters, right? And this is going to take longer because you need more samples to get accurate estimate. You see it, right? So action value and value, they are, of course, same mechanism, but you are estimating more parameters here because you are thinking about every single pair of actions and states, right? Everybody's clear, right? Okay, cool. Now, if you got that, then we have one mechanism which we look at the environment. We don't need the MDP anymore, and we get a rough estimate of the action values, right? So we can eventually do this generalized form of the policy iteration, which I'm calling it here Monte-Carlo policy iteration. So how does it work? This is exactly the policy iteration that we had before. The only difference is that, so this loop is exactly the policy iteration. So you start with one policy, you evaluate the policy, you improve it, right? And again, you got this new policy, you replace it here, you improve that, you evaluate that new policy, you improve it, and you keep on going till you converge to some stationary policy that is hopefully your optimal policy. Okay? But the key point here is only that we are using the Monte-Carlo estimation to evaluate your policy, right? Because we do not know MDP, we cannot do like dynamic programming anymore, right? The only thing we can do is just sample from the environment and average, right? Okay, now one thing that you might ask me here, I have written here greedy. I haven't written here improvement, right? So this greedy thing that I have written here is essentially the same improvement as we had before. So that is the same thing, right? So the new policy is basically I look at this action value function. I take the action which is doing optimal, right? In that sense, given what I have evaluated, right? So I look at the action which at the particular state is giving me the highest estimated value for action value. So it's the same thing. The only reason that I call it greedy is that now this action value function that I have here is not necessarily the true action value, right? It's an estimate of it, right? Meaning that for the given policy, I might be still wrong, right? So this Q hat of pi, it might be very different from Q of pi if my estimation is poor, right? So this is why I call it greedy, because you somehow think that, okay, you are impatient, you just do estimate given a few samples that you have, but you are impatient, you are too greedy, you just, based on those values, decide to just improve your policy, right? Everybody's clear? Yes? Okay, great. So now, this guy that you see here, in a very ideal world where you can really sample infinitely from your environment and your estimate is very, very accurate, this guy is okay. But in practice, we don't have that much of samples, and we don't have time to wait for so much episodes. So what we do, we usually are really acting greedy. Like we just estimate with few episodes, and then we decide to improve. And because of that, this idea is not the best idea. So some of you might have heard of the epsilon greedy approach. That is a kind of modification of this one, which we are going to do later in this chapter. But right now, based on the policy iteration, this is the kind of update that we do, the way that we improve it. Okay? So now, in this case, if you want to just compare this Monte-Carlo approach that we have here to the generalized policy iteration that we had in chapter 2. So there what I told you that we have one policy, and then we do evaluation, we get to the value function. That value function was giving us the Q function as well, right? And then we just improve it, right? Once we improve it, we get into the next one. And each time that we were doing the evaluation, we were just doing it suboptimally because we said, like, we don't want to wait for the dynamic programming to really converge. We just want to stop it at some point, right? And then it was just initially for some random policy that we start, maybe it was not very good evaluation, but gradually it was getting better and better, right? So the variance of changing was reducing, and eventually we were going to converge to the optimal policy. We are pretty much doing the same thing here. The only difference is that we are just using Monte-Carlo, right? We are using Monte-Carlo to do the evaluation, right? And this Monte-Carlo could be problematic, right? Because there, we were just terminating the algorithm, right? But here, we are estimating, right? This is much more noisy as compared to that one. No? And this kind of variance between the true evaluation and what we get could be high. But again, this going to show the same behavior. Like you start with a random policy, your evaluation is total nonsense. But when you start to improve it, it gradually is going to get better and better, right? And it makes sense. Like imagine that you have the whole entire world, and you want to walk in this world, right? So the initial policy that you evaluate, because you don't have so much samples, you cannot go everywhere in this world, right? Your evaluation is very bad, very poor, right? But once you narrow down your policy, you would say, okay, I'm going to just take this path, then you gradually start to collect more samples, right? Because you have reduced the space of your choices. You're just walking on that path, right? And since you are just walking on that path, you get better estimating of your value function, right? But this is coming at the cost of the chance that you lose some other optimal path that you're not really trying it at first, right? And this is why we are going to later do epsilon greedy. But for now, we don't really need to care about that. Questions? No question? Okay. So if you got no question, then just to wrap it up, so you start with some policy in this approach. You just use Monte Carlo to evaluate the Q function, and that Q function is going to land you at some other policy, right? So if you do greedy improvement, you're going to get into another policy. And you keep on doing it till you converge into your optimal policy. Now, here, there is no more guarantee that you converge to the optimal policy exactly, unless you are sure that every time you are using Monte Carlo, you have infinitely large number of samples, right? And by infinitely large, I mean like the number of samples that you have as compared to the number of states that you have is much larger. But this is something that is not going to happen in practice, right? And because of that, you cannot guarantee that you are really ending up with the optimal policy. Okay, so questions on Monte Carlo? Yeah.
So with the Monte Carlo iteration, we're evaluating the action value, not value.
Yes. I mean, in model free from no one, we always evaluate action value. Because we cannot really use that Bellman equation directly to estimate action value from value, right? Compute action value from value. Here, yes, it should be Q, right? I meant Q, right? Sorry. Yeah, it's better to put it Q. I'm going to fix it. No. Okay. So, no question? Okay. So, now, one thing that is happening here with Monte Carlo is that if you really want to use Monte Carlo, you need your episode to end, right? It means that when you are in one environment, you need to have a terminal stage, right? And that terminal stage should happen in a foreseeable future, right? If you have a world where there is no terminal, or you might play with a policy that does not end you up with the terminal very soon, then this is a problem, right? Because one episode that you're collecting from the environment takes forever, right? So this is one issue. So if you want to really sample, you really need to have a terminal state that somehow ends up your trajectory or episode. Now, what happens if you don't have such a thing? Well, you might say, okay, what can I do? I'm going to give a maximum amount of time, right? And then I terminate it. Meaning that I start from S0, I end at ST, but I stop playing simply because I don't want a longer trajectory, right? But there is a bit of challenge here. The challenge is that when you want to estimate so if you want to just collect your sample return, right? Your return going to be R1 plus R2 plus RT minus 1 plus RT plus what you would get after, right? But you are terminating. With a terminal state, everything is fine because RT, after that, you are always getting 0, right? So that is no problem. But here, when I get to RT, then after that, I know there is still some rewards coming. I don't see it anymore, right? Because I terminated, correct? So that is the issue. So the problem that you have is that, for example, if you think of GT minus 1, the reward that you get after T minus 1, this is RT plus whatever comes after that, but those guys do not exist anymore in your sample, right? Now, how can I do this in practice? So if I want to use Monte Carlo on such a thing, the idea is that I would say, okay, if I consider a small discount factor, then, or depending on the kind of discount factor that I have, I would say that at some point on, I am not too much interested on my rewards, right? Because if I am thinking of this T to be very large, say it is 100, right? And I'm talking about the sample return for the very first time, then it's going to be R1 plus discount factor times R2 plus discount factor to power 2 times R3, and so on. When it gets to RT, I already have gamma to power T minus 1, right? For the next ones, it's going to be gamma to power T. And it doesn't matter. Even if gamma is 0.9, when T is 100, that value is extremely small, right? So that is almost 0. So I can roughly say that when I think about the very first state, then whatever comes after the termination is not really impacting my sample, right? It's definitely much smaller than noise that I'm seeing in my sample, right? So what I can do, I can say that, okay, it doesn't matter really. So I can start from back very end and collect whatever I had, and then I take it for the value or action value of my first point in the trajectory, right? That's fair, right? But this statement is correct for this guy, right? This is not correct for this guy, right? You agree, right? So you cannot really estimate or take samples for the pairs which are at the tail of your trajectory, right? You can just do it for the first ones, right? So this is why we have this window W as well here, right? So I'm going to consider one window W, and this window is like the time where up to which, so W is something smaller than T. It's one of the time steps here in between. And that W is where I feel like anything after this W is fair to take. I mean, it's fair to ignore, right? But before that W, I can estimate anything before W. After W, I cannot really estimate anymore, right? So you do the same thing as before. The only difference is that you're not going towards the very end of your trajectory, right? You go up to times T minus W, and that time T minus W is going to somehow give you a fair window, fair buffer, that you can assume that for the very last pair you're estimating your trajectory, still the impact of termination is negligible. Okay? So this is one idea that you can do. This is Monte-Carlo by termination, right? But this guy obviously is giving you less sample efficiency as what you had with terminal state, right? Because in the case with terminal state, you could just walk on your trajectory, and every single pair on your trajectory was one particular sample, right? So you had one trajectory, you were using everybody inside the trajectory, right? But now you're throwing away a bunch of them in your trajectory because you know that they are not giving you reliable estimates, right? So this idea is not a very good idea. So this is eventually very sample inefficient. And what we can do to resolve it is the idea of bootstrapping. So